Now, this one I'm going to do a lot on the screen. It's kind of a volunteer lecture, so I'm giving myself a little bit of leeway. But it's also, all the details are in these notes. Okay? So anything that you see pretty much in terms of a calculation or a formula, everything is in here. Of course, last time I gave you that derivation of the Kirkwood Bachelor formula, which is not in those notes. Okay, but everything else, several examples are there. Okay, but the main thing to remember, of course, is the Fokker-Planck equation. I have some, I have particles, and they have position x. So at, so this is some representative position. This is the center of mass. So when you do this kind of coarse graining for the Bachelor-Kirkwood formula, you really just assume all the particles are located at that reference position in the middle of the box, and then you're just looking at the other conformational variables and how they're distributed. So at, yeah, there we go. I've been working on my mood all day. Okay, particles at position x. With conformations, and I'll call this some vector z. Okay, so z is a set of properties of the particle. So that describe, for example, its orientation. Say it's a growing particle, it might be, say, the particle length. Things like this. So some distributed property that you're using to describe the current conformation of the system. And then these conformations have some dynamics attached to them. Say you're having a rotation or some sort of process is making the length grow or the volume or something like this. And there may well be some sort of, you might model some sort of diffusive effect in this kind of configuration space up there where say the distension vector, you have thermodynamic fluctuations that are kind of making that distension vector kind of vibrate around, so you include some diffusive effect to capture that. So then you'll have some, so this could be a tensor right here, and then some grad z alongside. And that's just to make sure you get something that looks like a diffusion when you put it into the Fokker-Planck equation. Okay. Though if you're really starting from first principles, you know, you'd have some sort of ordinary differential equation with the noise term sitting here, and then you'd be taking appropriate limits. Okay. So then you have a conservation equation, psi t plus dx x dot psi with z dot psi is equal to 0, so you have a Fokker-Planck equation. And actually I should say, let me expand on this a little bit. So x dot typically will just be some statement that you're moving with the center of mass. So in the case of a propulsive particle, center of mass is moving with the fluid velocity, however that's being produced. Though if you have a propulsive particle, of course, it will have its own velocity, so there could be another piece that's sitting here in that center of mass flux of your particle. So, but in the case that we were talking about yesterday, where you have these dumbbells, then the center of mass is, the whole thing is being moved along with the fluid flow. Is x dot equal u plus some diffusive flux. Okay, so let's put that in. And typically, as I said in this Bachelor-Kirkwood formula, we are assuming that the gradient of u could be taken as a constant across one of these averaging volumes. Okay, and so the particles are moving against that gradient. So really, I should have written something like this. So it could depend on z, it could depend on grad u at x, so we'll have an x dependence to the grad u, and that kind of statement. And so then, of course, I need to have some sort of formula that recovers U and grad U from the concentration, namely how many particles do I have in a box, and from what their conformation is. How are they distributed? How is a polymer coil contracting and producing a stress in that volume? Okay, or if I have a swimming particle, how is it producing an extra stress by its motion along a particular direction? Okay? So that, of course, is where the Bachelor-Kirkwood formula comes in. And it says if I have some sort of more detailed model for the particle, some sort of microscopic model, like these two spheres connected by a spring, then you'll be able to evaluate something, this extra stress, in terms of this typical expression. Of course, I'm going to be turning it into, well, okay, I'll just write it down in terms of the sum over the particles, and then you understand that we need to take a distributional average after I write this down. Okay, and then take distributional average, which we did in the previous case for the dumbbell, right, where we had this R distributional average of R transpose, and that was the conformation variable, which just said in what direction is the polymer coil being stretched and by how much. Okay? So then I'll end up having some sort of integral aside against some kind of microscopic extra stress term that depends on the will give me some dependence on the conformation variables. Okay, now, so let's talk about, let me just kind of set it up a little bit. So here we're going to be talking about swimming rod suspensions. Okay, but that's kind of the background. That's kind of the theory background for this. And this is just getting back to the motivation, which I'm pretty sure that you've seen this in at least one talk. This particular movie or some movie like it. What this is showing is the roiling dynamics of tens of thousands of bacteria subless in a suspended droplet, actually a pendant droplet. And so, they're all swirling around in there, they're swimming around, they have plenty of oxygen. They're right near a free surface. That's actually a meniscus up there along the top. This comes from John Kessler and Ray Goldstein, when Ray was at Arizona, working very closely with John. So when they do PID on this particular flow setup, and so it's just bacteria and water. And so what they see are these kind of large-scale structures. They're about a factor of 10, usually larger than the size of the individual bacteria. And there are structures in it like vortices and jets. And for example, the jets are about an order of magnitude faster often than those of the individual bacteria. So you get these large-scale structures. They're not hugely scale separated, actually, from the individual swimmers. So it's that you have when you're deriving a kinetic theory, you're making all sorts of scale separation assumptions, right? You're assuming you have many, many particles. You're assuming that you can break it up into boxes that are small relative to the overall flow size, and you have many particles in those boxes. So you're making lots of scale separation assumptions, which are perhaps not what's really going on in this particular flow, but you are getting larger scale flow structures. So what you do is just kind of put your blinders on and you go ahead and you try to use a kinetic theory like that and see what you can get out of it. Okay, so the kinds of questions that you want to understand, these are far out of equilibrium systems. You're pumping energy into them all the time because they're swimming and metabolizing, they're swimming. So, but the questions you might want to ask are, are there conditions under which you will move from some, say, less structured state into something like this, for example, with volume concentration or with system size? How might the dynamics depend on the way in which the bacteria are actually actuated? So, bacterium, here it is. Obviously, I keep calling this the bacteria. You'll accept it after a while. So, they have their flagellar bundle at the back, so you could think of it as a rear propulsed little device. So you have something that's pushing from the rear, you have this flagellar bundle turning, it's pushing fluid back, so it's exerting a stress on the fluid in this direction. And then there's this guy's being pushed forward and has a compensating drag, right? Because the total force on this thing has to be zero. It's low Reynolds number flow, it's a free particle. Okay, so, but what if instead it were being pulled from the front? Okay, so we're a puller rather than a pusher. It turns out that makes a huge difference in the theory, though we're not quite sure how much of a difference it makes in fact, but it makes a huge difference in the theory in terms of what kind of flow structures and instabilities you can get out. It's a very, very big difference. And we see that not only in the kinetic theory, I'll also tell you about big particle-particle simulations, where we're not just doing a PDE theory. We actually started this whole game by writing a big simulator for a bunch of self-propelled rods moving around in a 3D box. Okay, so I'll tell you a bit about that. Okay, so, but this is just a little bit of something that you should always remember. It's extremely useful, and this is just local slender body theory for the Stokes equations. It says the following, that I have some sort of object in the flow. I've drawn it to have some curved aspect, and it's long and slender. So I take a cross section from this, and it's got some radius A. Got a length L, and so I have an aspect ratio epsilon is equal to A upon L. And we're going to assume that that is small. Okay? So this object, of course, there's a stress on its surface. It's exerting a stress as it's moving or being moved around in the fluid. It exerts a stress on the fluid, and all I need from that is the azimuthally integrated stress. Okay? So I'm not going to talk about a force per unit area on the surface. I'm going to talk about a force per unit length. So F, which is going to be a function, here, let's give myself a center line. I assume it's an inextensible object, so I'm going to use the arc length as a material variable in this case. And it has some force per unit length. Exerted upon the fluid. And it also has some surface velocity, which we'll take to be the velocity of the center line, actually. But let's call that V less T. And local slender body theory just says that to leading order in an expansion in the aspect ratio, we have the following statement. I know many of you have already seen this, but I'm going to make a few remarks on it anyway. It says that xt minus v of st is I plus xs transpose acting on f. That's my statement. That is an asymptotic reduction of the Stokes equations for the dynamics of this body. Okay? And I forgot something. There's a constant here. And this C is the log of E epsilon to the minus 2, plus or minus 2.
Sorry, what's I?
What's I? I is the identity. That's a tensor. That's a rank 1 tensor. There's that usual stuff again. Does everyone know what XS is? That's the tangent to the curve. I'm taking an S derivative, right, of position along the center line, so that's the tangent. So this is a rank 1 tensor formed from the outer product. Does anyone not understand what I mean by that? Okay? Okay, so, but this statement, this is what I would call an anisotropic drag tensor. This is going to tell you, given a certain force, what kind of velocity do you get out of it relative to the background force, right? And so if I have a force which is directed along the tangent vector, it has twice the effect in terms of the consequent velocity than if it's orthogonal to the tangent vector. And that's this whole statement. If I have a rod falling under gravitational load in a Stokesian fluid, it will fall more or less twice as fast along its axis if it's dropped in this way, rather than if it's dropped this way. Okay? And this is also the basis for kind of geometric nonlinearity that lets a slender body object be a swimmer under a force-free condition. Right? Because if this were somehow describing a swimmer, and I had this constraint that the integral of f was 0, then if this tensor were not here, and I took an integral of this equation to get the motion of the center, the velocity of the center of mass, say, quiescent fluids of this v were 0, I would get that it was 0. And it's only not 0 because actually I have drag anisotropy. Forces act differently in different directions according to the geometry of the body, and that's how things get around through the sun in some instances by shape deformations and over elemental flow. It's the drag anisotropy.
But what about spheres? There are spheres.
Well, those are not slender bodies, first of all.
Yeah. Well,
Yeah.
okay.
Let me just say that.
But there is no possible. There is no difference from the orientation.
Spheres don't swim by themselves.
Well, that's not so.
No?
You can take something. There are certain they're multicellular algae like Volvicella that are covered. It's just basically it's I think it's like glycogen or something. Anyway, there's a bunch of there's kind of a polymer matrix in the middle. It's a sphere. It's covered with cells, each of which have 2 flagella on it. And these guys kind of exert a tangential stress on the fluid, and they motor around quite nicely.
Yeah.
But maybe that's not answering your question.
It's still 0 force, right?
Yes, it's still 0 force.
The integral is 0.
The integral is 0, not the force. The integral is 0. The total force is 0. Okay, but this is a standard tool to be used in all sorts. This shows up if you're talking about, if you read Doi's stuff on passive rod suspensions, he's using something like this. If you're looking at, let's see, anything about, like settling rod suspensions, all these rigid rods, flexible rods, this kind of shows up as kind of a leading order theory. Now, let me just say, this term here is log. Okay, and there's some very nice work by Keller and Rubinow and then by Johnson, and you'll find it referred to in these notes, where there's a next order 1, non-local term. That captures non-local hydrodynamic interactions of this object with itself. So let me just say that as an asymptotic expansion, so Keller, Rubinow, and Johnson worked out this next term. It's like a regularized Stokes limit.
That's not Lighthill?
Well, there is a version due to Lighthill. I favor Joe Keller. He's one of us from the Cron Institute. So, before he left for Stanford. Who was this Lighthill guy? I have no idea. So, but there's this non-local term, which you can work out in different ways. And Lighthill had a way with an integral cutoff rather than this finite part integral. And at any rate, the main thing to notice is that in terms of the asymptotics in the small parameter, there's not a big separation between a log term and an order 1 term. So those non-local terms can become important very easily. That's just something to remember. Log is not a big asymptotic separation. Okay, fine. So, now, let me just, okay, so you've seen all this kind of thing. Here's a pusher particle, there's a puller particle. Now, so this is almost all this is joint work with David Santillan, who when we started this was a postdoc working with me at Toronto, and he's now in mechanical engineering in Illinois. And what David had done in his thesis at Stanford is he had built a very, very efficient numerical code for solving for the hydrodynamics of thousands of settling slender rods through a fluid, through a Stokesian fluid. To look at the kind of coherent structures and instabilities you get if you just start off with some suspension of rods and then they just start to settle. And so that actually got him some nice prizes. It was a very nice piece of work. But the way to think about it is that it's a huge n-body problem. Okay? So what he was doing is he was solving the Stokes equations in the exterior of all of these rods, and all the rods had to talk to each other through the Stokes equations. Now the Stokes equations have no time derivative in them. Okay? Essentially it's a biharmonic problem, if you like. And so what that means is you can really think of solutions to the Stokes equations as solving a boundary value problem at each time step. And when you have objects moving through it, you're solving this boundary value problem, and kind of the boundaries are changing continuously. And so that makes it very nonlinear, because the solution to a boundary is, you can just take the Laplace equation, right? You're solving the Laplace equation in the exterior of some sort of object that's giving some sort of flux or a Dirichlet boundary condition, and you're trying to find the harmonic field in the exterior. The solution, while the PDE, Laplacian U is equal to 0, that's a linear PDE, but solutions to it depend non-linearly on where the boundary data sits. So if you put a little notch into your boundary data, that's not a linear change in the solution. It's a nonlinear change. So all of these kinds of problems, which are many-body problems in the Stokes equations, are very nonlinear because solutions depend on where the boundaries are. And here, it's all these rods, and they're all changing constantly.
Well, I see that the flow depends non-linearly on the boundary, but does the dynamics, the statistical properties of dynamics depend non-linearly on the position?
Yes.
I could imagine that it would not, right?
Well, think of it as like a bunch of self-gravitating of bodies in a gravitational problem, right? So gravitating bodies have a bunch of planets, have 100,000 planets. So that's that kind of problem.
Okay.
It's nonlinear because kind of the fundamental solutions to the PDE you're dealing with have algebraic singularities.
But don't we still
like the
find the same
gravitational
statistical properties? Like the density fluctuations?
Well, that you have to solve the problem to find out. I'll talk about that. Yeah, I'll talk exactly about that. So that's a very interesting question. Okay, but what we did is we built a model for rod-like swimmers, built on top of his numerical method. Okay, and so here's what the model looks like. I'm going to go through the derivation for a much simpler model as the basis for the kinetic theory, but I just want you to get the sense of it. So here's a rod-like swimmer immersed in a Stokes fluid. You're solving the Stokes equations, and what you're seeing is the velocity field around that swimmer. Okay? And so the way this swimmer is being actuated is that it's moving in this direction. Here's the posterior half of the swimmer. And what we're doing is that on the swimmer surface, we are just prescribing a tangential stress. Okay? We're just saying, this swimmer exerts a prescribed tangential stress along that axis on the fluid. So if you like, it's like thinking of this Volvicella, this multicellular glob, this sphere, this algae. And it has all these flagella, and you could do kind of a coarse grain of that, and you could just think of it as a tangential stress being exerted on the fluid, and that's what's moving it around. So that's what we do. So and you can see, when you solve the Stokes equations in the exterior of it, you have a velocity that is pushing fluid back along this region. Okay? This, if you like, is the is the capsule, it's the cell body of our rod-like bacteria. There's a no-slip condition here. That's the payload. That's what's being pushed by the thrust element. And so now it's moving upwards with some velocity, and it's dragging fluid with it. Okay, so that's the velocity field you see around it. That's typical of a so-called pusher particle. Okay, so the pusher particle is fluxing fluid back through its propulsion, back here, and pushing a payload forward. So it's dragging fluid up and pushing it down. And that creates around it an extensional straining flow, which you can see there. This is a three-dimensional solid. You just see it in slice. Now, this is a polar particle. Now it's fluxing fluid down the anterior half. This is the payload, which is being dragged up. So fluxing fluid down, dragging fluid up, it creates a compressive flow along the particle, but they're both moving in exactly the same direction and actually at the same speed. Okay? Now this is a particle which Tim Pedley calls the stealth swimmer. Okay? So this is just a particle where we've coated it everywhere with this prescribed tangential stress, and it's moving itself along at some velocity. But the difference that it has from these other two is that if I have a force-free particle, then kind of generically, except for in special cases like this, you'll have that the velocity field die-off comes from a force dipole. And that looks like 1 over r squared. Okay, so in the suspensions of pushers and pullers, or pullers, the interactions are through velocity fields that decay like 1 over r squared. Okay? In this particular case, this is actually a quadrupole, which means that its velocity decays like 1 over r cubed. Okay, and they don't interact very well with each other. So we don't pay, who wants to do the cases where there's not a lot going on. Okay, so now here's a simulation. And I know I have a student of Ramaswamy in this place, and we did this simulation because there was a prediction on whether if I had an aligned suspension of swimmers, in fact it was for the particular, it could be either pushers or pullers, but if you had a line suspension of swimmers, that you could not maintain kind of a flocking order, a long-range orientational order. Okay? And so now we've taken 2,500 of our swimmers. They're in a 3D box with periodic boundary conditions. We've lined them all up, and we've just randomly displaced their center of masses, and we're just going to let them go and see if they can stay pointing up. Okay, so there it goes. And what happens is it develops, you can see a wavelength in there somewhere, and you can see it develops an instability. It does not like to remain with long-range orientational order. So, and what does it go into? Well, it goes into kind of a Royling flow, which is reminiscent of what you see in the experiments of Kessler and Goldstein. Okay? If you look at the background, now what's happening, of course, the other way to think about this is I have all these kind of force generators in the fluid, and they generate a velocity field, which moves all the other force generators. Okay? And so they're all moving around in the velocity field that they are creating by their motion in interaction with everybody else. And, you know, it's very time dependent. It's roiling around. If you look at the background velocity fields, we'll look at a bit of that if I remember to unhide the slide. Then you'll see there are things like vortices and jets and all those kinds of things. Okay, so that was kind of the first result, which seemed to be qualitatively aligned with experiment and seemed to verify theoretical predictions of Simon and Ramaswamy. And I'll say a bit more about that later. So some of the things that we found, and we've done a lot more since then, is that while you destroy the long-range orientational order, we do find that you maintain kind of a local order on the length of a rod. Okay? And I'm going to say a bit more about this because this kind of effect, for example, depends very much on whether you're a pusher or a puller. Now, why might that be? If you go back to this picture, here's a pusher particle. And so I have a flow that's looking like this. Around it, that's its local flow field. If there's another such particle co-moving with it, then ignoring the effect of interaction, these accept through their fields. That was kind of the basis of that model that Jerry Gulliver wrote down, actually, when he was trying to simulate calamity. Then you can see that they will tend to attract and align each other through these types of flows. On the other hand, if you have pusher particles, they will tend to decorrelate in direction. Okay. So, but these simulations I just showed you are pusher particles. And here's a background flow field that comes from it. And so you can see there's a vortex, there's jets, also things like this. And I'll say a bit more about suspension velocities and stuff like that in a bit. Okay, now, the one thing you cannot do with a big n-body simulator is you cannot ask it very easily analytical questions. Okay, it's hard to query, get an inequality or anything like this out of it. So we decided we were going to try to develop a kind of a kinetic theory, kind of very much along these lines. And so it's really, what we've developed is really just a version of what's called Doi-Rod theory. If any of you read chapter 9 or chapter 10 of Doi-Edwards, how many of you have a copy of Doi-Edwards? Excellent book. It's a really excellent book. I know Kayla has one. So what we developed is a special case of Doi-Rod theory, which talks about the dynamics of passive rod suspensions. Okay, and in the special case where our rods have active components. Okay, so it's not a liquid crystalline type theory. Okay, it's more of a rod suspension theory. So in some ways it's going to be quite different, I think, from the motivations of Ramaswamy originally in terms of these kind of symmetry considerations, and also from what, in terms of the types of instabilities that you see, says Joni. Yes.
So I still want to connect it to Jeffress's lecture. So the length scale that comes from this instability, the length scale of this instability is exactly the same length scale that he derived in connection with the Frederick's instability.
That may be, but actually that's not so, because he has a Frank constant.
Yes, but there is a diffusion here, the diffusion of the particles. So that comes from the Frank constant there.
No, if you want to think of it, I mean, that's one way to think of elasticity. I mean, you have to figure out what your Frank constant is from that. But on the other hand, we also find that we get how do I want to put it? We get instabilities out of this system in the lack of diffusion in the kinetic theory, a purely hydrodynamic one, where you don't even have to account for diffusion. So it's got some differences. And it's really not a Friedrichs type instability.
Yeah. His is also, it's actually not a Friedrichs type in his case also. I think
It's not in this case. It is in his. I mean, by his own words. I mean, when he was, well, he was sitting there, I leaned over and I said to Becco, I think he's calculating a Friedrichs transition. That's what it looked like to me.
No, actually it is also a flow transition that comes from the PP term in the U equation, in the velocity.
No, the source is the same. The source is the same, but the Friedrichs transition also depends very much on the boundary conditions that you have on the system. And that was also the case with that calculation. But the source of the instability is the same,
Yeah, but the length
destabilizing source.
The length scale does not depend on the boundary condition he has.
Yeah, okay. That's, I guess that's true, but I still claim that the physics of it is quite different. Okay, so here's a very simple case. Okay, we're just going to be using, here again is this slender body theory again, is the basis for it. And we're going to use slender body theory to construct the particle fluxes for two, just position, and then the conformational variable here is just going to be the orientation of the rod. Okay? So in this case, the rod is going to be swimming with some direction t, and it's going to have some position x. Okay, so it goes like this. Here's my rod, right there. It's coated with a propulsive stress along its posterior. So that's pushing back. So there it is right there. It's that little blue thing up there, I guess. And it has a surface velocity, it has a force per unit length it's exerting on the fluid, and then has a no-slip payload to the front half. Okay, we take slender body theory, there's my various constants that I was talking about. Now look at a pusher. And the other thing that you assume is that the size of the swimmer is small relative, it's again the same thing, you assume it's small relative to the size of the variations in the flow field. So you can consider it as moving in a background linear flow. So there we are. We take our velocity field, we linearize it around the center of mass. So x of s, of course, is just the center of mass plus arc length back and forth, plus or minus L over 2 along the axis. And then on the posterior part, if you are going to have a propulsive stress, you have to allow yourself the degree of freedom to have a slip velocity on the surface. If you don't have a no-slip condition, you have you're specifying part of the stress, so you have to give up a degree, you have to give yourself a degree of freedom. In that case, it's a slip velocity along the surface, plus some other stress to satisfy all your boundary conditions, like it's a rigid rod and so forth. And your surface velocity, you write, again, is center of mass plus a rotation plus the slip part. Okay. Oh, I'm sorry. So this is yeah, I kind of said that in an ass-backwards way. That's the propulsive stress. Pointing back, there's a kind of correction. If you're being rotated, you might have to determine some constraint stresses. And then your surface velocity is center of mass plus the rotation piece plus a possible slip velocity on the surface. And then this is just a no-slip condition on the rest of it. And then you have a zero force, zero torque condition. So it turns out you can solve that problem analytically very easily, just sticking that all into the slender body approximation. And there you get that motion at the center of mass is the background fluid velocity evaluated at the center of mass, let me use this thing, plus the velocity that comes from its own propulsive mechanism along its axis. So even in the absence of the background velocity, of course, this guy swims by itself, just goes along. Is U naught, you can express in terms of the propulsive stress, and in terms of kind of a normalized viscosity from slender body theory, which you can write as the length over the real shear viscosity times the geometric coefficient. And then what you also recover for the rotation is just the classical Jeffreys equation. Okay. Do we know what Jeffreys equation is? No? Okay. So Jeffreys equation shows up generically when you're looking at slender rods in a background flow, background linear flow. Okay? So it's just like that equation that we wrote down for the dumbbell. We had r dot is equal to grad u r, right? That was that part in the rotation and stretching induced by the background flow for the dumbbell. And there it is. P dot now is grad u on p, but p is an orientation vector, so its length doesn't change. And a consequence of that is you end up with this projection that pulls off any length changes, essentially. That comes from the rotation and stretching induced by gravity. Okay, so there it is. So I dot this with P, well, that's just 0. So P dot P dot. P transpose P dot is 0, okay, because P doesn't change. Okay, so those are the single particle fluxes. Now, along the way, what you've solved for is the surface stresses on the rod, on the no-slip part in particular. And you know what the rod position is and orientation, so you can use now the Kirkwood formula in a slightly different form. So instead of having a surface integral of I have it kind of transposed around, but instead of having a surface integral of position times surface stress, for a rod it just becomes an integral along the center line. Because the surface stress, force per unit area, gets replaced by force per unit length. So you can calculate all of this, and here's what you find, is that the extra stress induced by a rod moving in a constant linear flow has two components. This is the stress that comes from that induced just by it swimming by itself in a quiescent fluid. Just the solo stress. This is the piece that arises from the fact that to remain straight, this rod has to develop stresses to keep from being bent by a rotating flow or a stretching flow. So this is what you would call a constraint stress. Okay? And it's fourth order in P. Now the thing about this particular stress is it depends on grad U, of course. And if we're looking at a theory where grad U is being developed entirely from the dynamics of the rods, then that grad U turns out to be higher order in terms of volume concentration, so we're going to drop it. Okay? We could include it actually, we get a very interesting Stokes equation if we included it. But we're just going to keep this piece. Now notice, okay, so there it is. That's the sum over this average volume of all these pushers. And it has that same form, PP transpose, as you saw for Oldroyd B, which looked like RR transpose. Okay, except that now P is constrained to have length 1. And it has a strength that comes with it, sigma naught, which is lost somewhere on this page somewhere. Oh, there it is. Some geometric coefficient, its length cubed times that motive stress again. Okay? Now, let me just tell you, oh, here's polars. And you can see, they have the same form, they come with opposite signs in terms of this volume average stress. Okay? So, this is the form that you see for Oldroyd B, where you have a positive thing times RR transpose. Okay, so in terms of kind of the sign of the induced stress relative to this kind of dipolar form, this PP transpose RR transpose, is polars that look like a typical model of some sort of dumbbell suspension. Now, that makes sense. How does that make sense? I distend a dumbbell. What does it do? It comes back. It creates a flow back towards the center. Right? If I'm looking at a polar particle, I have to turn this around. And so it's kind of, if you like, it looks kind of like that is associated with the contraction of these dumbbells for a stretch spring. Okay? So this is what it looks like, if you like, Oldroyd B. But this is a huge difference. You're saying that the sign of a stress changes its form. That's a huge, huge difference. And of course, that's this whole thing about extensile and contractile stresses, as you see right here again. Okay, then you have your kinetic theory. There's your particle fluxes, where we've added on center of mass and rotational diffusion, some normalization on the Planck equation. We couple that, of course, to the Stokes equations for these average velocity and pressure fields that I'm going to be solving for this divergence free condition. And there's my distributional average, okay, for the extra stress, where now I'm just letting the sigma naught have the sign that goes with being either a pusher or a puller. Okay, so I'll give it a sign. Now, so I have a sigma naught here, some sort of stress strength, I have a velocity, I have a system size, which I haven't, obviously I have that. And it turns out that there's a nice way to non-dimensionalize this problem, where you can express all kinds of interior PDE coefficients in terms of geometric quantities having to do with the swimmer. And so if you take just the swimmer speed as the characteristic velocity, and you construct a characteristic length by scaling the swimmer size with this quantity, which is the effective volume fraction of swimmers. What is that? That says, here's kind of the volume that a single swimmer takes up. If I just think of about a rod of size L, and I rotate it around. And this is the total number of swimmers, that's the number concentration over the total volume. Okay, so what this is saying, take all the swimmers, multiply by the number, I get some volume. You take all the swimmers, I have this L/2 cubed volume. I multiply it by the total number, so I get some effective volume that they take up, then I divide by the system volume. That can be greater than 1, less than 1, whatever, because they're rod-like. And then it turns out that with that scaling, this sigma naught goes to a purely geometric coefficient that has to do not with the scale of the stress, it just has to do with the size of the swimmer and what his particular geometry is. That sets U naught to 1, and you just end up scaling the system size by this new characteristic velocity. Okay, now it turns out that this system also has a nice property, a nice energetic quantity. Okay? Configurational entropy. So psi is a conserved field, its total value is conserved by the dynamics. Okay? And since that is the case, it turns out that if you normalize psi by its value for when it's in the flat state, namely just an isotropic uniform state, in our scaling that turns out to be 1/4 pi, and you form an entropy from it, you do that integral, so you have to integrate over all the position and configuration variables. That turns out just to be a positive value. It only reaches its value of its minimum value of 0 if it's in the uniform featureless state, namely just an isotropic uniform suspension. So this is kind of an energy-like quantity. It measures the size relative to 0 of fluctuations from being in the featureless state. And it has a very interesting dynamics, this thing. It tells you a lot about these systems. If you look at the time derivative of this configurational entropy, it comes with 2 contributions. One is you reduce the size of fluctuations and hence the size of the entropy because of diffusive processes. Right? And these are these guys. Here I have my translational diffusion, my rotational diffusion. That draws down fluctuations. But there's a piece that comes from the work being performed on the fluid by the swimmers. And is proportional, since it's a total work term, actually input power, not work. Then, through the Stokes equations, it gets balanced against the rate of total viscous dissipation. And what happens is you end up with an alpha, this kind of signed, rescaled stress term, sitting in front. And so it says the following. If alpha is positive, which is the case of having polars, which are like the passive rod suspensions in terms of the sign of the extra stress, this guy is strictly negative, so this whole right-hand side is definite in sign. And fluctuations will monotonically decrease. That's what that says. It's an exact statement. It's not some linear theory or anything like that. It says the size of fluctuations will monotonically decrease. And it will just go down to a uniform isotropic state. And that is what we see. Now I'm going to show you what happens when you look for this kind of prediction in the case of having many particle simulations, not kinetic theory. It turns out that this is what we see as well there. It's very interesting. Pushers. Pushers, that term is negative. So this can become a destabilizing term. Right? So if I have some sort of gradient in velocity, did I say what E was? Does everyone know what E is? I said it was the rate of viscous dissipation. Right? So it's basically grad U squared. But that's just the symmetric rate of strain tensor, contracted against itself. Sorry. So E always is. Unless you're doing Maxwell or something like that. Okay, so the point is, this is grad U squared. Sorry. And so if I have then a velocity perturbation, inhomogeneity, it drives up fluctuations. Okay? And so you can then have a feedback loop between diffusive processes that are trying to pull fluctuations down and things like this pumping of energy into the system, in the particular case of pushers, they're trying to push fluctuations up. And so what you see is you get some sort of statistical equilibrium where these guys are just kind of oscillating around if you actually do look at the entropy in these systems. Okay. Now, here's a very useful special case. Just so you can get your hands on what these equations really look like. So take the particular case of just having a local concentration times an orientation field that has a single direction at each point. Okay? So a distribution in P now is just this delta function in some direction n. Shove that into the kinetic theory and you can do an exact reduction to get PDEs for this local concentration and for this local swimming direction. Does that make sense? Like that? Okay. You can even answer the second question. But and here's what you get. You get a conservation and transport. Okay, so here I'm dropping diffusions, otherwise I can't close these equations exactly the way I have. So do that. And so I just get a conservation equation for the concentration field. It's moved around by the sum velocity that comes from the background velocity plus the particle motion. That moves the concentration field. And then the end field, again, is vectored by n plus u. And then I have this Jeffreys term that has to do with the way the gradients turn n. Okay, so I have coupled transport, nonlinear transport PDEs. You see things like this coming out of Leslie Erickson. They can have a certain kind of flavor. They can look like that. And then I have my equation, my Stokes equation that generates the velocity with my extra stress, which is just this alpha, this sign stress strength, local concentration, and then the usual kind of n transpose. Okay, so there we are. Now, what's useful about this one is you can look at a particular case. So, which is going back to the theory of Sinha and Ramaswamy, where, oops, what happened? I guess I just said the same thing again, but there's a special case where you can just look at a uniform suspension all aligned in the z direction. Now, I want to look at linear theory for that. That's a special steady state solution. So I can linearize my equations for that case, and I can find dispersion relations for the growth rate as a function of the angle of a plane wave perturbation to being aligned in this one direction. And what you find is you have two branches of instability as the function of the direction of a plane wave perturbation. And what the form of this turns out to have, a very nice form, namely that if you have one mode that is in the right half plane, or rather is in the left half plane, so you're stable on that one mode, necessarily the other mode is in the other half plane. So no matter what the angle of the perturbation is, then you're always unstable. Because one or the other of the modes is going to be in the positive half plane. And it picks up the Ramaswamy and Sinha have one branch of this, which we pick up in a particular long wavelength. Picks up their branch. But we pick up another one that actually agrees with what we see in our numerical simulations. Namely, we have instability in any direction of the plane. So in that sense, it kind of captures the Sinha and Ramaswamy theory as a long-wave version of our theory. Okay, and then this is just showing that we do get, let me not go into this. It's just to say, when you go to the rod suspensions and you look for instabilities as a function of a direction of a plane wave perturbation to the orientation field, we find that you're unstable all angles, which is nice. Okay. Now, but once you've dispensed with the aligned case, okay, you know those are always unstable. Okay, so forget about them. They're not interesting in this case. What is interesting is the one that shows up naturally from this configurational entropy identity, which says natural states to look at are when the configurational entropy is 0. Right? And so those are the uniform isotropic states. And so that has a very interesting kind of stability aspect to it. So now instead you look at the stability of the uniform isotropic state. And it turns out that you can reduce that particular problem. So I take the uniform case, which is 1 over 4 pi. So I have a uniform concentration, and in any box I just have swimmers that are pointing in all directions with equal probability. I add on a plane wave perturbation onto a plane wave in space, and I can generate a eigenvector relation that has my growth rate or dispersion constant sitting inside of it. And it turns out to be kind of an integral equation that arises because of the Stokes part, the non-local Stokes inversion of the velocity field. And that generates an eigenvalue relation for you. You solve that eigenvalue relation. It's been done by various people, David and myself. We looked at it in more detail in a later paper with Crystal Illuminator, as well as Subramanian and Koch, slightly after us. The main thing is that what you find is that for pushers, this is what the stability diagram looks like for the growth rate as a function of wave number, modulus of wave number. You have at long waves 2 branches of instability. As you move up in wave number, it collapses down onto 1. and then this actually comes down, and if you have no diffusion in the problem, this branch terminates, and you no longer have eigenvector solutions beyond this point. Okay, so you have kind of a finite branch of solutions, unstable solutions, that are described by an eigenvalue relation. Now, if you take polars, this whole thing just gets flipped over, exactly. Why is that? If I just told you this is the stability diagram for pushers, and I take polars and it flips over as exactly the same function, just with a minus sign, why might that be? I'm saying that there's something very relates polars and pushers.
Space if you turn it 90 degrees, the flow field.
Yeah, it's a reversibility condition. If I simply take a pusher, it's got a motive stress like that, and I reverse the sign of that motive stress, it becomes a polar. Okay? So there's a reversibility in this whole thing. So basically, if I flow forward with instability for suspension of pushers, and then I turn time around, or I change the sign of the stress, it would just go back along its paths in a stable direction. So there's a reversibility in these systems. Okay. It's kind of creepy. Okay. Now let me just say a little bit more about this. It turns out that this linearized equation is interesting, and you can reduce it even more than, with crystal, we reduce it even more than we had done in the Santiago and Shelley paper. It turns out that the linear stability of this problem can be reduced entirely to the dynamics of the first azimuthal mode on the sphere. Okay, so I have a p-dependent dispersion relation. And it turns out that the only thing that matters out of that is the first azimuthal mode on the sphere in terms of the stability or instability of the whole system. So you can just reduce, without going into an eigenvalue assumption, you can reduce it just to something that involves an integral transform against these kinds of things in terms of the polar angle on the sphere. It's just the first, this is just the first azimuthal mode, so m equals 2 going around. I guess that's the m equals 2. So that's telling you something immediately, by the way, having just said that. If the whole instability is being governed by an azimuthal mode on the sphere, do you think you have concentration fluctuations in linear theory for this system? No, you don't. Okay? What this is telling you, to think about that a little bit, is that in this system in linear theory, you do not have any concentration fluctuations. You don't have the growth of concentration fluctuations. The instabilities that are in this system are orientational instabilities in terms of the directions of the dipoles. You have a perturbation, they'd like to line up. Okay? But there's not a dynamics in linear theory that says they're going to concentrate. Okay? And so anyway, what Christelle and I did is we analyzed the high wave number behavior of the linear theory using Laplace transform arguments and showed that it was kind of a controlled dynamics. Even though you didn't have an eigenvalue relation to solve up there, you could solve that problem at high wave numbers and show that it was nice in a certain sense. I don't want to say too much about that. I just want to take a look at the PRV last year. Okay, now here's another interesting thing. I lied to you a little bit. I said that if you made this particular choice for the characteristic length, you could eliminate that length out of all the kind of PDE relations. That's not quite true. If you kept translational and rotational diffusion, that characteristic length shows up in there. If it's gone out of the stress, it's strengthened out of the velocity. But it turns out that if you go back to our suspension, or rather our rod simulations, then and you measure the observed diffusion, these rods have a rotational and translational diffusion. Rotational diffusion scales with volume concentration, approximately linear way until you get up into what's called the semi-dilute regime. So what does that mean? So I have a rod swimming around, and I'm just looking at the sphere, and it's doing some sort of diffusive behavior on the sphere. And that rotational diffusion scales linearly with the volume concentration, that means there's something like pair interactions, right, that is dictating that. That's not quite pair interactions, but it's going up linearly. And it's behaving, the translational diffusion is really that just comes, just compare with the classical result of Brenner, that says if I just have a rod that's moving at some velocity, some constant velocity, but has a translational diffusion, there's a consequent, it has a rotational diffusion, it has a consequent translational diffusion because it's always changing its direction. So, and that is inversely related to the rotational diffusion with a certain constant, 6 pi or something. And so that's actually what we observed to very good accuracy in our simulation. So what we find is that if we make that assumption that the translational diffusion scales inversely with volume concentration and the rotational diffusion linearly, then you can eliminate the volume concentration completely out of the problem except for into the renormalized boundary conditions. In that case, our theory gives us a very nice stability threshold for where that branch is going to cross the axis, okay, for pushers. And it just depends on two things. The length of the system divided by the length of the swimmer times the volume concentration has to be greater than some kind of geometric value having to do with swimmers and the alpha, the size of the element. Okay, and so then what it predicts is that the kinetic theory that predicts that for our swimming suspension, then a volume concentration is around 0.9, kind of approaching the semi-dilute limit. It's kind of the edge of where we really think our theory is applicable. There should be an instability, but I'll show you now in our simulation we get around 0.5, which is not bad. In the factor two. Okay, so, let me show a few simulations now. What does the theory actually do? So this is Kayla did this nice movie for me. Turned off her chemotaxis. Thank you, Kayla. So this is then starting with a nearly isotropic suspension. So the rods are kind of willy-nilly pointing in various directions. And in the kinetic theory, we're kind of solving for a pseudo kind of effective particle dynamics, which is defined, just to visualize it for you. And what you're seeing here on the right is going to be the concentration of swimmers. Yes? No.
No, the chemoattractant.
No, there is no chemoattractant in this. You don't remember doing this one for me. Okay, let me just tell you it's the concentration of swimmers. Okay, so there they are. So they're forming these jets and vortices. It's very featureless. You're not seeing any real concentrations. And maybe we won't because I'm completely wrong. But yeah, I guess it's nothing. It's just green. Nice background. So then what you see is rather like what I showed you in those rod simulations in the experiments. You see kind of a roiling flow, lots of vortices and stagnation points and things like that. And dynamics in the neighborhood of stagnation points, as I say, is always an interesting thing to be interested in that more. And variables. That's what the kinetic theory does. So here, this was the growth of an instability from near isotropy, okay, for a pusher suspension. And here's some of the long-time dynamics that you see out of this. Was very interesting, and at least in these 2D flows, and you see a version of this in 3D, which David and his students have done, is you end up getting your jets in the background velocity field, and you have shear layers sitting in this that are associated with concentrations, actually, of the swimmers. I'm not showing that here. And these kind of shear layers will break up transversely, and there you see it breaking up, and you have vortices, and they'll reform in the other direction. So this whole dynamics is a kind of quasi-periodic formation of kind of concentration bands are associated with shear layers, and then they break up transversely and go in the other direction, changing position, phase within the box, and just cycling through this over and over and over. So that's very interesting because that's a version of what we who've ever played this game in fluid mixing call kind of a stretch fold dynamics, right? If I have a band which is transversely unstable and you start to stretch it out and it goes in the other direction, you're stretching it and folding it. And those are typically very good mixing flows. so homogenized, if you like. And so, so this is a simulation that David and I did of the mixing of a scalar field that's being moved around by the background velocity of the simulation to just. Okay. So this is just a color field. And I just realized I forgot something, but I'll get it right now. So there it goes. That's the instability developing. And then you can see this kind of stretch fold in the motion of these kind of fluid layers.
Is this for pushers or?
These are for pushers. Now, I didn't show you any polar stuff. The reason I didn't show you any polar stuff is you start off with some large perturbation, it doesn't matter, you have this entropy relation. And that tells you it's just going to die. And that's all they do, they just die. They just go back down to the uniform state. Now, this enjoys some popularity on the web. Unbeknownst to me. So you guys were looking for fluid dynamics t-shirts, right? You can see I've searched for it many times now. We'll go to images here. Ah, there it is. There's your fluid dynamics t-shirt. Pirated by some bozos out there on the web. Now,
Not even just one, all of them.
oh yeah, this is really good. How much time do we have? Okay. We're starting to hit the end, but let me see. Oh, you may also like. Yeah, here we go. You see, you can get your Chihuahua shirt. They have fluid dynamic thong. So you can get a thong. It has my picture sitting on it. We would like to have it. So anyway,
Have you ordered it?
I'm sure they're doing it Christmas. Well, what I was going to do is I was going to write to them and just say cease and desist, or send me one sample of everything. And they have like 30 different things they've posted this image onto.
You claim them copyright.
Yeah, no, that's right. Well, the copyright is owned by me and David and by APS. Or no, AIP, I think. So I think, they certainly would go after it. Unless David gave it to him and never told me.
He has like 50 thongs in it.
So look, I'm just going to get on to, I'm just going to text him a message on my BlackBerry and just say, send me a thong. See what happens. Okay, so, eat that fun. Now, oops, oh yeah, okay. Okay, so here, now what I wanted to do was to then go back, and we've recently gone back and looked in more detail at the rod simulations. We have these predictions from the kinetic theory, not just in terms of instability, but in terms of other things. So the first thing I want to show you is just a series of simulations where all I'm doing is upping this effective volume fraction and looking at the dynamics of the suspension. Okay, that small volume fraction, S nu is equal to 0.1, which should be in the stable regime for being isotropic and uniform. Okay, so you don't see anything correlated going on, but maybe there's something very subtle that you're not seeing immediately or develops over very long times. But let me just say by any statistical measure that you can kind of, no, not any, I'll show you some statistical measures perhaps.
There is
where-
periodic boundary condition
Yeah,
everywhere.
the periodic boundary conditions. So that's another interesting question. Sir?
You don't have any hydrodynamic interactions, but these things just have passing through each other?
Oh, good question. So in some simulations, we include a local repulsive force so that they can't pass through on collision. At these volume concentrations, any collision between the particles is actually very rare. So this is actually a 10 by 10 by 10 box, and you're just looking through the volume.
Yeah, even though your average volume fraction, yeah.
Yeah, I mean, we don't think it's an important
Yeah.
factor.
Yeah.
So the sticks really aren't intersecting, it's
No, it's just because you're looking at a projection. They're not going through each other. Okay, so then you up it to 0.5, And then you start to see something that looks a little more correlated, maybe. You see some areas of more clarified fluid relative to maybe some concentrations. And then you go up to 1, and then you can definitely see structure in here, and things that look like number of concentrations and things like that. And roiling around, you have this look, this kind of strong local order. It's very dynamic. You want to scale the box. And this are pullers. And pullers just don't do anything. So when I was about to say that in this case, it's hard to find any signs of being away from uniform isotropic, that's not completely true. In terms of things like their occupancy statistics, it looks Poissonian, pretty close to Poissonian. So I'm just kind of randomly throwing down positions. But you do see that there tend to be local correlations still when two rods get close to each other, they line up and become locally non-isotropic. Here, you don't see anything that looks like the emergence of anything that goes away from isotropy, uniform isotropy, as far as we've been able to do.
So Mike, some of the earliest work on collections of microbes were for chlamydomonas and bioconvection. And so why do I seem to see or remember that there's order, there's large-scale motion?
That has to do with overturning instabilities of Rayleigh-Taylor type in those cases. So what happens is a clammy, if I remember, is a little heavy. It's swimming up, though, towards the light, and so they concentrate at the top. And then you get a local Rayleigh-Taylor instability because your local density is
And they
high.
also concentrate because they swim towards downwelling regions because of their being guided by the vorticity.
Yeah, so that's in their interaction with the flow. Yeah, that's right. But it's just a different kind of thing. Gravitational effects are big in those, and you get these plume-like things, and that has some kind of Rayleigh-Taylor stuff.
So you mentioned that pullers are analogous to the Oroid B fluid
Yeah.
dumbbell, right? But then in the lecture you said the turbulent mixing was induced by under force. So how do you
I'm just talking about in terms of let me put it this way. If I just take a unforced Oldroyd B fluid in the Stokes limit, then there's an energy law that you can write down again in terms of a relative strain energy, and you'll find that just decays monotonically unless you're forcing it somehow. Okay? So here, the forcing is interior, if you like, but you would only see this kind of mixing stuff in the presence of external forcing. Otherwise, it's just relaxation. It's actually in the notes. If you want to see that statement, now that you say it, that is on page 75 in the notes. You take a look. Properties of the Oldroyd B system and the Stokesian limit. And so this big epsilon that you see is actually a relative strain energy. So it's just saying how distended on the mean square average is the system, how strained are the polymer flows. And so if you set the F to 0, then that's just a pure dissipation. Just relax. That wouldn't happen actually if for some reason you had that opposite sign. Instead of RR transpose, it was minus RR transpose. Then that one term looks like integral D squared would have the opposite sign. And that's what's happening with the pushes. Okay, so we'll get through this in the next few minutes. It's getting late. But so then you can look at things like number density fluctuations. Okay, and so what you do then is you take interrogation boxes and you put them down there, and you have an expected number of particles in an interrogation box of a certain size, and you say, well, how many do I have actually, and what's their distribution? And so what it should behave like is just a uniform occupancy that you're just kind of throwing down into the box. It should behave like a Poisson distribution where this bracket n is just the expectation of the number of particles in that box. And so then what we see is that if we have polar suspensions, here, they behave Poissonian up to high volume concentrations, high volume standard simulations. On the other hand, we end up having broadening tails. So concentrations, if you like, broad tails, when we're looking at pusher suspensions. And we can pull a power law out of that, which gives us tails that scale like the expected value to the 0.6, which is bigger systematically than that you get for Poissonian, but it's less than that is for giant number fluctuations taken by Simon and so on, I think in the same paper. So we're seeing somewhat weaker fluctuations than have been predicted in theory. Okay. So you do see fluctuations in concentration, and these fluctuations are associated with two things. They're associated with, well, actually having higher velocity. And so here is showing a local concentration as a function of velocity of swimmers. As you find that high velocity swimmers tend to be associated with locally higher concentrations. So you have the packs. Yeah.
So is this a simulation in 3D?
Yes.
So it's almost close. It's 6.6 is the predicted value for 3D. It's 2 by 3.
No, it's actually higher than that. You're
2 by
thinking
3.
of another, we can talk about that. It's more around 0.8. If you're actually looking at the standard deviation, it's 0.8. Okay, we had to kind of recalculate things a little bit for what we're looking at. So, and then what's also associated with is local alignment. So what we have are are number concentrations, which are packs of rods, higher concentration moving at higher velocities. Now, these are not fixed membership objects. You know, they're constantly kind of going in and out of these little fluctuations. So it's not like you have a school of fish that are kind of hanging along with each other. Now, the other thing that's interesting is actually the maximum velocities that we see for swimmers, so 3 to 5 times bigger than the single swimmer speed. So these are kind of speeds of these jets. And it's kind of getting into the range that they see in the experiments. Okay, now you'll like this. This is even better than what's on the t-shirts. So then we looked at the same kind of mixing as we did in these 2D kinetic simulations. And so what we do is we just take a bunch of colored particles and we push them around with the velocity field. We take many, many, many of them. And then we just remap the color back onto the vertices of the grid and then make a plot of that. So here's low concentration. Now, what's interesting about this is pushers, is that this is mixing that's just induced by basically the uncorrelated motion of single swimmers dragging fluid around. They're just moving in random directions, and they're just dragging a bit of fluid around with them, and that's giving you a slow diffusion of this kind of sinusoidal variation. And that is what you see with 10 times as many swimmers when you're talking about polars instead. And so you see you don't have any large-scale flows, you generate still this kind of one-dimensional structure in the dye field, but it's diffusing out. Now, that certainly doesn't look like an incompressible flow field, and it shouldn't because we're looking at a slice through 3D. Okay? But there it is. And then this is what happens at the high volume concentrations. You have large-scale flow instabilities which kick in and then just start mixing this thing. This is what they should have had on their t-shirt. It's nicer. It's less kind of crystal, because you're slicing through this 3D thing and you have all these discrete rods running around. It's kind of a rougher object. It looks like a flame. Okay. And so what we can do is, it's interesting because one thing I didn't really go through here is that there's actually, when you look at various quantities, for example, if you look at the particle diffusion, swimmer particle diffusion as a function of volume concentration, you really cannot see any signal in that. I told you it was looking, the translational diffusion was looking inversely proportional to volume concentration. That's already saying, I was already implying that you're not seeing any sign of the transition in something like the diffusion of the individual swimmers measured through a diffusion. If you take a look at an object that's associated with rotations that would be inducing translational diffusion, like the L2 norm of grad u squared, right? Because I have Jeffrey's equation, which is essentially governing the rotation. So if I look at the integral of grad u squared, then, or square root of that, let's give it the right scaling. Then you see little if any sign of a large-scale flow transition in that quantity. But on the other hand, if you look at other things, like the rate of mixing in this system is measured by something called the multi-scale mixing norm, there's a pretty clear bifurcation for the case of pusher suspensions. At around 0.5, you start mixing the fluid. You get a change. You have very slow mixing in the case of low volume fraction pushers or any sort of polar suspensions. If you look at tracer diffusivity, so passive tracer diffusivity, not diffusivity of the bulk of swimmers, then you see very clear volume concentration effects, and you see a bifurcation. So plainly, there are things that are not being captured well in the kinetic theory. Okay, it needs think about how to put finite number of fluctuations into it these days. So, and then, so then you see around 0.5 again, you see a sharp onset in the size of diffusivities of passive tracers in the system. You get onset of mixing and diffusion of passive tracers. If you blow up this region around here, then this is the slow, essentially linear increase of diffusion in the polar suspensions that's just associated with rods kind of pushing things around. Okay, then those are other things. So I'm going to stop there. This is a good time to stop. Okay, so this paper is going to show up in Royal Society Interface sometime in the next month or two, something like that. If you want a copy of it now, for those that are interested, I can give you. Okay, so that's the deal on active rod suspensions, kinetic theory, and comparison with particle simulations. Certainly in all these complex fluids types of problems, it's very nice to have in your back pocket not just one way of looking at a problem, namely with the kinetic theory, but also to have some other method, usually a particle method where you kind of get to look at the micromechanics in detail and see what it says. Now, of course, the kinetic theory is derived under lots of assumptions that are, for example, not being met by our particle simulations, right? I mean, do we have scale separation when we have a swimmer of length 1 in a box of size 10? Maybe, maybe not. We probably really need to be looking at larger boxes and more particles. And Keva's working on some efforts to do that, actually, kind of particle simulations that are kind of halfway between a kinetic theory and a particle simulation. So, the other thing that's very interesting in this, too, is this, of course, it shows up in these active gel type problems, but the idea that you have this destabilizing stress is associated with having these extensile flows around the particles. And there are other types of problems that of that sort that show up that don't have to do with locomotion. So, for example, if you go with active gels, I mean, there are bacteria that will grow into long strings, and they're just constantly bifurcating, constantly having cell divisions along the strings, so they're kind of stretching strings in fluid. And that's actually, again, an extensile flow that they develop. There's also, along these strings, there's also problems that have to do with, Peter didn't talk about this, but phase transitions where you go from a smectic to, or rather from an isotropic to a smectic state. And if you like, the crystal that you get out of this phase transition, the seed, it's going to be the global solidification, is actually a tube where the molecular layers are lined up, pointing out from the axis. And so what that means is, and then what happens is that they grow in length for various reasons. They grow in length, but they fix the number of molecular layers. And so they have a permeation current going into them, so the whole thing is stretching out and dragging the fluid with it as it's growing. So I also think that some of these microtubule dynamics problems that have to do with bundling have this kind of dynamics associated with it. So anyway, that's a big thing in all these active systems is the extensile versus the contractile stresses with the pusher types inducing instability. Okay, so anyway, thanks.
Do you know what's the rate of growth of those synaptic filaments?
Well, that's an interesting question. Since they are fixed in width and they have a constant permeation current going into them, that means that they grow exponentially in time. And that's what you actually observe. Actually, let me show you a little movie. These are really beautiful. It's a really beautiful problem. Of course, I could hit this little bar down here on the right, and I just go to the desktop. I've got all this fuss. Filaments. This is from Peter's experiments, maybe 15 years ago. This is the growth of a smectic filament. And this is a single filament. If you actually go measure the length, it's growing exponentially fast. Now, what's interesting is that there's all sorts of buckling instabilities that happen in this system. And so actually when I did a lot of work on developing tractable numerical models for looking at suspensions and flexible fibers. Yeah, oh, these are the spaghetti monsters. So something else happens. They just start sucking everything up. Now there's something else, I think he's going to go to a new one. There's a new one. But this is very characteristically what goes on. They just grow like that. You get these. This is all taking place in a little layer of fluid, in a microscope under a cover slip. And so they're confined. These little patterns are confined to lay in this layer. So they grow. They're kind of 2D space-filling patterns. They grow. But I really started developing all these methods for dealing with flexible fiber suspensions because I originally worked on this problem.
What are those?
I think they coalesce, and that's what happens. That's what I think.
Well, yeah, I mean, kind of, but like, what's the structure of the smectic inside of there is maybe a little less clear. Focal conic domains. Okay, so let me just say a little bit about this problem because it's interesting. What you have is this tube, actually it kind of seeds as a little thing like that. And what's presumed to be the structure inside of here is that you have all these smectic layers that are kind of lined up like an onion skin, a long onion skin around the axis. What is that? And then you have a permeation current of liquid crystal molecules going into this smectic phase and kind of shoving themselves down into these layers, and then the whole thing is growing. Now, if you're looking at one of these layers, a bunch of liquid crystal molecules lined up, you bend that layer, that's a splay, and you can have a bending response to this thing. So this is really just like a bending beam. This is really a bending beam, and it comes from the splay response of the molecular layer, which is bending. And so, in the hands of a fluid dynamicist like me, what this is this stretching elastica, which has non-local interactions with the rest of itself through the fluid, because hydrodynamically it's approaching itself all the time through this growth. Now, what's driving the instability? Well, if I take a little piece of this, it grows in time by some exponential factor. And one way to think about this is that each little element is growing at this exponential rate, and as it's growing, it's dragging fluid along the outside. It's being permeated in, but it's also dragging fluid. So it drags the fluid despite the growth. And what that's going to do is create a compressive tension inside of this beam. And if it grows fast enough, that drives a buckling instability. And so you can analyze this. You know, if you know what the elastic constant is and this kind of stuff, and the rate of growth, you can predict that there's going to be a buckling instability in this system. And there is. And then you can write a code, and this is where I developed all this non-local slender body theory for elastic fibers. For those of you who've ever looked at any of these papers of mine, like with Annika and Horner. But let me see if I have a movie, because they're really quite pretty. Let's go to one of my other 100 movies, or 100, well, maybe I won't do this one, because it will just take too long. Let's try this one. This is actually going to be my talk on Thursday. It's about a completely different line of work, which has to do with flapping and wings and all these kinds of things. But I think somewhere down here, yeah, this is a terrible thing to do in the audience. I apologize to you. Oh, there it is. Of course, it's not going to play. Okay. This is way back when you made a movie, you had to put a title on it, you know, because it was a VCR thing that you stuck into a tape, into a machine. So you have this kind of picture. But let's see if this actually plays, or maybe it won't. Enable content. Okay, but you can see what happens. So what you're seeing here is the growth. Now we're doing closed loops. You can also do open loops, but it turned out easiest to do closed loops at first. Let's start with the easy stuff. So you start off with a closed loop like that. It starts to grow and it starts to buckle, and then you form these patterns. Actually, we were able to get much more intricate ones than that, but that's what the movie would show, would be a more intricate simulation of how these patterns grow through kind of buckling and smoothing. And it looks a little bit like Sackman Taylor, but it's a different physics. So anyway, did I answer your question? The other questions?
Are you going to talk about any of this flapping stuff on Thursday?
So on Thursday, I'm going to talk about two things. I'm going to talk about flapping flags, why flags flap, how they flap, those kinds of things. And if you want to do some reading beforehand, there's an annual review article this year by myself and Jim Zong on this topic. And the other thing I'm going to talk about is flapping flight. And so the thing that's very interesting about flapping flight is that you can interpret it as arising out of a symmetry breaking bifurcation in the system and Navier-Stokes equations. If you want to, so flapping flight turns out to be an attracting state that arises from symmetry breaking instability. And so I'll talk about that. It's very pretty stuff. Okay, see you tomorrow.